But I put it back last time. I am a no trace teacher. Never know I'm here. Okay. Just see if I can somehow get this thing to connect. Of course, now it will work. I think it almost literally just takes connecting it to the HDMI and then disconnecting it. There's my family, but that's not what's on my screen. So
it's probably using it as a second monitor, so if you drag it to the side, it should be.
let me know if it changes.
Hey Adam, are you on break?
No.
Oh, sorry guys. I'll go back to you.
You'll probably have to change the display settings to mirror, because right now it's probably using it as a second monitor.
Oh, that's what I'm on right now. That's what I'm clicking on. Okay. So I don't get that. Got to connect it like that to make it work. Okay. Turn off. I'm just going to turn off. Okay, you guys can see that all good there online, right? Okay, so we're still talking about navigation stuff. Some of this stuff we've kind of talked about a little bit already. Let's see here. So we're going to go over kind of the different navigational facility stuff again in a little bit more detail. You two listening? Or what are we talking about? Okay.
Please share with us.
Yeah. What's so important? I can't wait till break.
Cost of iPads.
Okay. Okay. So navigation systems. We talked a little bit about NDB last time we were in class. Does anybody remember what an NDB does? Non-directional beacon. Basically uses radio frequency, but this is kind of the stuff that we're going to go. We're going to look at NDBs, VORs, DME, RNAV, GPS. We will look at that. We're going to look at some of the other systems that are in the airplane that we use as well, and then we're going to look at and jump into instrument approach systems as well. So let's look at traditional navigation systems, starting with the NDB. Just a quick recap from what we looked at the other day. NDB is a ground-based radio transmitter. Transmits radio energy in all directions, and it goes on the frequency band 190 to 535 kilohertz. Signal travels as ground waves, penetrates obstacles, and sky waves, which is refracted by an ionosphere. So basically it just means that it can be bounced off of clouds and things like that. So, and as far as what you guys need to know, just know that an NDB is a ground-based transmitter. You guys don't need to necessarily know all the basics, the radio bands and all that stuff. Just know that it is a type of ground-based navigational aid. And once again, too, you guys will have this PowerPoint on the files as well. So in case you want to review it later. But that's all an NDB is. It's just a type of ground-based navigational aid. And it's kind of more outdated. We don't really hardly use them anymore. But if you were to get asked a question, which I believe the next quiz, so I'll try and do a better job of narrowing down the quiz for everybody for next week. So I can tell you this. Next week we'll have a question on the quiz. It'll say, name 3 different types of ground-based navigational aids. NDB would be one of them. But as far as any more details than that, you're not going to necessarily need to know anything more than that.
Just basic stuff.
Basics, yeah.
Are you going to do another study guide thing for week 3?
Yeah, I'll try and
That'll be on it.
yeah. So the instrumentation in an airplane that's used to pick up an NDB is called an ADF. Now, so what we have that we just saw an NDB. You're gonna take pictures of it all? You'll have the PowerPoint, so you know. So we look at what's the ground-based receiver, and then the next thing we look at is what is the instrument in the airplane that actually is used to pick up that particular ground-based navigational aid. So an ADF is in an airplane, and it's what picks up the NDBs. Okay, like I was telling you the last class, it just basically points to where the NDB, where the signal is coming from, and then you follow that in the airplane, like you navigate towards it and kind of follow the needle. Has an antenna. I mean, you have the receiver and the indicator, so pretty basic. Don't really need to know much more than that, but that's what an ADF is. It's an automatic directional finder, and it picks up NDBs, signals. Radio magnetic indicator. These things are not really found in many of the modern day airplanes. It's not really found in the airplanes that you're going to ever be dispatching. These are types of things that are really found more in, like it says here, found in high performance aircraft. But it basically picks up, it'll pick up NDBs or VORs. So it kind of is a combination of the two. That's pretty much all you need to know about that. It's not really common to have an RMI, but if you do, it picks up VORs and NDBs. This here talks about how an ADF navigates. Really, there's nothing on this slide that you necessarily need to know, and we already kind of talked about how they pick up the NDB signals, so I'm just going to skip through it. VORs. So we've talked about VORs, but what that actually stands for is very high frequency omnidirectional range. It is a ground-based nav aid, and it is currently the primary navigation aid used by civil aviation. The ground station itself, wherever it's located, is oriented to, that MN stands for magnetic north. Has anybody ever heard the term magnetic north? So you have two different types of north. You've got true north and you've got magnetic north. Does anybody by chance know the difference between those two?
They talked about it on the video.
They did?
Yeah.
Yeah.
Magnetic north is a little bit off. You go like the poles.
Yeah, exactly. It's due to the magnetic variance of the poles itself, depending on where you're at. There's always going to be a little bit of a variance on what your receiver in your airplane thinks, or your heading indicator thinks is magnetic north. It's going to point. So like if you were to point it north and just keep flying north thinking that you're going to reach the North Pole, because of how the magnetic variance shifts as you get closer to the poles, or further side to side, that it'll start to like pull you into a different direction. So once you get really close to the poles, it's like those things are pretty inaccurate, because it's not it's going to like take you in circles essentially, once you get close enough.
I think they said west is best and east is least, and that's subtract or add.
Yeah, and you'll want to remember that, not from the standpoint of that you'll need it on a quiz, but we refer to that little phrase all the time in dispatch. So most of our stuff that we do is already is converted to magnetic north. But yeah, so like right here in this area, I want to say we're somewhere between
14.
Yeah, it's in the teens, yeah, like between 12, 13, 14. So that's if you were to take 0 degrees being true north, magnetic north here would be like minus 14, minus 15. Yeah, I mean, there's some you get up there though. I mean, it's, you get up into like Seattle and stuff, and it's, like minus 20 or something. So it does have a variance there. So all of our wind reports and things like that we get are all converted to magnetic north. So, well, I shouldn't say it like that. Let me backtrack real quick. When you get a wind report, the rule is that if it's spoken to you, it's in magnetic north. If you read it, it's in true north. Now, as far as a dispatcher is concerned, you're not going to really ever care about whether it's, the only time you ever care is when you do manual flight planning. Okay, that's the only time that you'll ever, as a dispatcher, truly care about magnetic north or true north, or what the wind report is that you're getting, if it's in true or magnetic. Because when you do, outside of this class, once you get qualified and get your license, you'll never do manual flight planning again in your lives. So this is kind of a one-time thing where you'll actually know what it is and be able to calculate the magnetic north variance. But after that, all of that stuff is automatically calculated on our software at work. So you don't ever have to do that. So here's in a situation like this is the only time you'll ever need to actually calculate it. But when you are at work, though, the only time it ever comes into play in a real life dispatch scenario is when you're looking at a METAR and so like the runway headings as an example. So like when they build runways, they obviously number them, right? So like out here at the airport is runway 19, and then the opposite end. It's just one runway, but it's, depending on which direction you land, it's either runway 19 or it's runway 1. Okay, but it is 1. It's always going to be the 180 opposite though. So the other end is always going to be 180 degrees opposite of the opposite end. So even though it's one runway, you can land pointing, runway 1, or if you're headed to the south, you would be landing on the 19 side. So those runways are numbered based on magnetic north, though. So runways are always magnetically aligned. But if you were to go read the METAR for St. George, and the wind report in the METAR was to say wind 190-15 gusting to 20, the METAR is going to be in true. So why it is like this, I don't know.
That's every airport.
If you read it, it's in true. If you hear it, it's magnetic. So if a pilot is flying down the canyon and he tunes his radio into the ASOS for St. George, he's hearing it. The ASOS is going to be in magnetic. The METAR, if he prints it out on his little printer from his ACARS machine, is going to be in true.
That's really weird. How far off are they as far as like, it's only like the land headwind?
That's where you would have your variance. So like John was saying a minute ago, St. George is more or less minus 14. So when going back to what Scott was saying though, west is best, east is least. So if you let's see. So if you're, this is best, I'm just trying to remember because I don't look at it that much, but basically when you look up magnetic variance, you can look up any airport, and when you bring up the information for an airport, one of the first things it'll tell you, it'll tell you the airport elevation, and then it'll tell you the magnetic variance for the airport. If it has a minus 14, all you're doing is you're taking whatever wind you're reading and minus 14 degrees off of the wind. So if it says 190, minus 14 degrees off of 190. And it will always be the same. So you'll just know that, if St. George is a minus 14, well, it's always going to be a minus 14. So that part of it doesn't change, but you need to calculate the wind difference, though. So the only time you ever need to do that, though, is if you're trying to calculate it in your head, like, well, let's see, is this going to be like a tailwind when he's landing, or a headwind, or if you're talking to a pilot on the phone and he wants to know what the wind is and you're pulling up the METAR, well, then you would need to know the variance in order to actually give him what it truly is. So if a pilot is talking to air traffic control and they give him the wind, same deal, that's going to be magnetic because he's hearing it. But a dispatcher typically reads it. So what a dispatcher sees is normally going to be normally going to be true. What the pilots see is normally going to be magnetic. So why it's just not automatically converted for us, I don't know. Just one of those things that it's kind of like the whole Zulu time.
Yeah.
There's several of those little concepts, but just is what it is.
So the METAR is magnetic, right?
A METAR is you read it, so it's in true.
Okay.
Yeah. Anything you read is true. The only difference, though, is that, like I said, if you're using the software at work to do flight planning, and you pick a runway that they're going to land on, that software will automatically do it. So you're not having to do this for every flight. It's really very limited that you would ever be calculating magnetic variances. And like I said, it would have to be a situation where pilot calls you up on the phone, you're looking at a METAR, and this is obviously before he even leaves for his flight. He wants to know, sometimes they're concerned with the wind before they even go. And they want to know, well, how bad is the wind? Are we going to be able to land? Some airports that we go to are only, you can only land going in one way and take off coming out the opposite way. So some airports, you don't have the option of landing on the other runway if the wind shifts. It's always going to be the one direction only. So if the wind isn't favoring, or if it's too much tailwind or too much crosswind, then you can't land. So there are situations where it comes up, but normally very limited. And if you saw it or dealt with it more than once or twice a year, then you're just extremely unlucky. So back to the VORs. They're aligned to magnetic north. So when they're sending out those radials, like those beacon, radio waves out on each of those radials, those are all those radials that you're picking up in the airplane are all magnetic north, or aligned with magnetic north. So the variance is already accounted for. So it provides 360-degree azimuth information accurate to within 1 degree. Transmits radio beams, which are the radials. It gives you course guidance. VOR information is not influenced by aircraft attitude or heading. It's used for ground-air communication. It has automatic monitoring systems. It has a Morse code identifier and a voice identifier. Transmits every 15 seconds. So if a pilot, what that means is if a pilot is tuned into a VOR and he's navigating based off of a certain VOR, the way that he can tell if he's tuned into the correct VOR is there's a little volume button on the VOR receiver in the plane. He can turn that up, and every 15 seconds it'll actually play the identifier, or it'll give you a Morse code. It'll do the beeps. So if you'd have to know Morse code, obviously, to figure that out. But then after that, a lot of them will actually say, this is the St. George VOR. So they'll say it and they'll have the Morse code. So the reason why that they have those on there is because sometimes VORs, they try to obviously limit, each one has a different frequency that you tune into. However, sometimes if you're up high enough, you might have 2 VORs in the same area that are on the same frequency. So it could be picking up the other one that you don't want, and so that's how you know, is by turning up that volume and making sure. The frequency range is 108, from 108 up to 117.95.
We're talking about the distance of VORs, like a high VOR is 140 miles, right?
130, yeah.
130, and then the low one was 45 or something.
Yeah, the lows are, yep, terminal is 25, low is 40, and high is 130. And there's a slide for that on here too. There's a couple of different VOR types. There's just a standard VOR. There's VOR with DME. And basically that just means it's a VOR that actually provides the distance measuring equipment. So when you tune into it, your VOR receiver, you have to have DME capability in the airplane, but most airplanes do have DME capability, but it'll tell you the distance that your airplane is from the VOR. But that's only if the VOR has the DME technology. So when you look at VORs, they'll either just be a standard VOR, or they'll be a VOR DME, or they'll be what's called a Vor TAC. A Vor TAC is essentially just a VOR DME, except that the TAC side of it is used for military purposes. So it's just a VOR that is both used for civilian and military navigation. So when you see VORTAC, just know that really for you, it's the same as a VOR DME. The TAC part is just that military also uses it. So but you don't necessarily need to know, you just need to know about VORs in general. So that's what it looks like on a map. On the navigational charts, we've obviously looked at them a lot last Saturday as well. So
I had a question about the markers. It said in the box, my understanding is if you have mileage in the box, that's from VOR to VOR. And if it's outside the box, bless you, you've got, that is between intersections, is what I understood.
Correct.
But I was looking at Sky Vector, and there's little markers, like if you look down at the bottom of this right here, there's, the little triangle right there. What is that? 'Cause that's not a VOR, but I got distances between the VOR and that.
That triangle right there,
Yes, sir.
that is an intersection.
That's an intersection.
Yeah.
Okay, I was thinking intersections had to cross.
Oh yeah, no, they don't. An intersection is just simply a point along a jet route or a Victor route.
Okay.
So yeah, in this case, an intersection is just, it's a point along a route like that, but it's identified off of, yeah, I mean, like for instance, the way that you know, like if you are, see this is the Bryce Canyon VOR right here, and if you are navigating south and you're going to this, what is that, Cassier intersection? So the way that you know that you're at that VOR, or sorry, that intersection. So like if ATC were to tell you like, go to the Cassier intersection and then hold at the Cassier intersection. If you just have standard just VOR equipment in your airplane, the only way you know that you are at that intersection is that as you're flying away from the Bryce Canyon VOR, your VOR receiver will tell you that you're flying away from it. And see this radial right here is 161. So your VOR will tell you that you're on the 161 radial flying from Bryce Canyon, which means you're flying away from it. And then your DME equipment will tell you 42 miles. So once your equipment says that you are 42 miles from the Bryce Canyon VOR, and as long as you stay on the 161 radial, that's how you identify where the Cassier intersection is. That's with DME equipment. Now, with an airplane that does not have DME equipment, then you need to have a second VOR come into play. So if you don't have the thing that actually tells you the distance, then the second way that you can identify this intersection is you track the 161 radial flying south from the Bryce Canyon VOR, and then you tune your other VOR receiver, and most planes have 2 or 3 VOR receivers. So you tune your other one into the Page VOR, and once the Page VOR shows that you are at the 261 radial, along with your other VOR receiver saying that you're still on the 161 from Bryce Canyon, when those two meet, that's how you know you're at the Cassier intersection. If you don't have DME. If you do have DME, then really you just need to track just the outbound Bryce Canyon 161, and then once your DME says 42 miles away from it, then you know that that's that intersection. So that's how you find intersections if you're in an airplane. Going back to what you were asking though too, so like this is an example, that box right there says 65. So that's the total from this one to this one. So it's between VOR to VOR. So this one here says 35 for this leg, and then this one here says 30, and then the combined is of course 65 from VOR to VOR. So one that doesn't have an intersection like this one that's 88, it's just, that's all there is. It's just VOR to VOR there. So here's DME. Determining distance from a ground DME transmitter. It operates on ultra-high frequency UHF radio band of 962 to 1213 megahertz. It's found in a VOR DME, a VORTAC. It's found on ILS systems, localizer systems, which we'll look at here later in this PowerPoint. It uses a paired frequency of nav aids. You tune into the VOR and it automatically selects your correct UHF frequency. interrogates the VOR station, which transmits a responding signal. It measures the elapsed time between both signals, and then it gives you your distance. The receiver calculates the slant range distance, time, ground speed. It's accurate to within a half nautical mile or 3% distance, whichever is greater. The limitation on a DME is going to be line of sight and slant range. It can be once you get at lower altitudes, the error can be higher or lower depending on the altitude, basically. And then it says it's negligible when it's greater than 1 nautical mile for every 1,000 feet AGL. So it's really, once you get really close to one, or once you fly over the top of one. See, one problem that with a VOR DME system is if you are flying at 35,000 feet over a VOR, then your DME equipment is never going to tell you that you're closer than like 7 miles because you're 7 miles straight above it, right? So once you get high enough and you're, right straight over a VOR, it becomes less accurate. So anyway, that's none of that is, necessarily stuff you need to really know. You just need to know what DME is. Just telling you the distance between the plane and the ground station. That's all you really need to care about. And there's DME arcs, which are for instrument approach procedures. We don't really look too much at this stuff or ever use this stuff too much. It's basically used for planes to align themselves with a runway for a landing procedure, and that kind of stuff we'll see here as we get more into the approach plates and things like that. But it's still very rare even to see one of these arc things. So just listing it in here because it exists really. These are VOR volumes. So this is kind of going back to what we were talking about with the standard, the high altitude, the low altitude, and the terminal VORs. So you have the 40 for the low, 25 for the terminal, and then 130 is the high altitude. So, and it basically is just showing, like on the high altitude one here, it's showing that if you're really, really high up, it has less of a range. See, it's 130 nautical miles up to 45,000 feet, between 18 and 45,000 feet. If you're below 18, then it's a little bit less, but none of that stuff you need to really know or remember. Just if the basic thing you need to remember, a high is 130, a low is 40, and a terminal is 25. This is what a VOR in an airplane looks like. It's comprised of a receiver, an antenna, an indicator, CDI needle. It basically will point, it'll tell you to or from. That's that little thing that'll flip-flop. So whichever one the arrow is pointed towards means you're either navigating to a VOR, or if it's down here, from the VOR. This basically tells you if the frequency that you're tuned into is unreliable or not. That's the thing that basically will switch the frequency heading around. Most of this stuff you don't necessarily need to know how to use it. You just have to understand what the VOR is and how it works, not necessarily what it looks like or anything like that in the plane, but it's just showing you a picture just to kind of give you an idea. They tune it in. They have a standby frequency for each one. And then there's the little knob to turn up the volume, things like that. So,
Has a new one.
what's that?
It has a new one.
It does? Where?
It says King.
Oh. Where? I'm not even seeing. Oh, right there. Yes. They made me change that. I don't know if I told you that or not.
Is it?
They've made
Then
me.
why did they include it?
Because they did it before they knew. So, long story. I'll tell you. I'm sure most people probably aren't interested in hearing it. Stupid. This is called an HSI, Horizontal Situation Indicator. This isn't really something that we look too much into, or even it's not something that you really need to know about. Just kind of covering it. But it's just a combination of navigation information using a VOR localizer. It uses multiple systems basically to figure out where you're horizontally situated. So it kind of gives you an idea, and it does the work of several systems basically. It's pointed to does the magnetic correction for you. And yeah, I mean, really not too much you need to know about this. So instead of overloading your brains with it, we'll skip through it. That's what an HSI looks like in a glass cockpit. This slide here is talking about in order to test your VOR system in your airplane, you can tune into that frequency there, and it will basically, you can run a test and see if your VOR is working correctly. Oops. Okay, so now we're going to get into the GPS stuff. If you guys want, you can take a break though here before we switch over. We're switching from ground-based to satellite now.
Oh man, they didn't get your mustache conversation on the recording.
Oh, they could hear it.
On the recording.
Yeah, it won't be like if you rewatch it, it wouldn't be able to, but okay, so now jumping into satellite-based navigation. So if you were to get a question on a quiz, specifically next week's quiz, about naming a couple of different types of satellite-based navigation, these next ones that we look at would be the ones you'd want to name. Starting with RNAV, which is area navigation. This type of navigation allows a pilot to fly a selected course to a predetermined point, which is called a waypoint, that's that WP, without the need to overfly ground-based navigation facilities. It allows direct or optimum routes. RNAV equipment includes, and when it says VOR DME, it just basically means that it can utilize ground-based navigation as part of its calculation if you want it to. It doesn't have to though. But VOR DME, LORAN, which is just a type of local area navigation, GPS, and INS, which is inertial navigation system. So you don't necessarily need to know those definitions, but RNAV equipment can determine aircraft position and track, ground speed, DME, and ETA, estimated time of arrival. RNAV advantages: time and fuel savings, reduced dependence on radar, and it more efficiently uses the airspace by providing optimum routes and altitudes. So RNAV is very widely commonly used now. And yeah, it's a lot more efficient than using these, you can think about all those VORs, you can think about looking at SkyVector and jet route, doing these zigzags that we're having to do. Well, this kind of takes a lot of that out of it because you can go to direct points that are satellite-based fixes, or intersections and waypoints, as this calls them, that aren't having to depend on having an actual VOR on the ground functioning, things like that. So
this mostly commercial airlines will be using this?
Yeah, commercial.
Locations?
Yeah, commercial or, higher end aircraft. So even if it's private, it would be more of like your private jets and, things like that. So kind of gives the example here, like, where you can go direct between 2 points instead of flying down and over. Advanced Navigation Systems, GNSS, which is the Global Navigation Satellite System. It's a constellation of satellites that provide a high-frequency signal that is picked up by a receiver. The receiver triangulates its position from satellites from the GPS system. Works the exact same way that, like if you have a GPS in your vehicle, or handheld, or on your phone, or whatever, it works the same. Aircraft have this global navigation satellite system technology. Regular GPS is the global positioning system, satellite-based radio navigation. GPS broadcasts a signal. Aircraft receiver tracks multiple satellites, determines the aircraft's position. Satellites are unaffected by weather. It covers globally. So you got global navigation coverage. Obviously, like, you can understand why that's better than VORs just off of just that one point alone. You're not going to have VORs out in the middle of the ocean. But you can pick up satellite, obviously. It covers oceanic airspace in remote areas. GPS uses VFR en route and terminal navigation, IFR en route, terminal ops, and instrument approach procedures. So it can do any type of navigation, like whether you're flying en route, whether you're flying a landing procedure or a takeoff procedure, which those landing and takeoff procedures we'll learn about later coming up. But it can do any of those things. It can replace any ground-based navigation. So once again, a lot more efficient. This talks a little bit more about the GPS system here. 24 satellites, and I think there's actually more now. I think there's more like 30 something. But you have to be able to pick up a certain amount of those at any given time. A normal GPS, I believe, like on your phones, I believe has to have 3 satellites in order to triangulate a position, minimum. Airplanes are required to have, I want to say it's 7 or more have to be in view in order to make sure and double make sure and triple make sure that it is accurate.
Does GNSS need 7 also?
Yeah, any of the satellite-based stuff needs, and I think there's actually a slide. I'm not sure if it's 7. I'm just kind of throwing 7 out there, but we'll look at it here in just a second. But there's a minimum amount of satellites that it needs in order to be able to use it. So, but we'll look at more of that in just a minute because there's a specific rule that goes along with that, being able to use it. So, GPS function, concept of ranging and triangulation from satellites to form a reference point. Receiver measures the distance from the satellite. So this has minimum 4 satellites to actually yield a 3D position. Now that's not necessarily the one that's the rule for airplanes. That's just in order to actually get a position. And it gives the DME, the bearing, the ground speed, and the time. Then this last thing here says RAIM availability for IFR, and RAIM is what we're going to look at here in just a minute. RAIM stands for Receiver Autonomous Integrity Monitoring. So what RAIM is it's basically So just so you guys know, RAIM is not an individual type of satellite navigation, okay? But RAIM is a system that monitors the amount of satellite signal in a given area at a given time. So if we are going to use GPS or RNAV or the GNSS, any of these satellite navigation systems, we have to do what's called a RAIM check for our intended route of flight. And what the RAIM check does is it goes through and it looks at our route, and then it tells us how many satellites. And so this is saying right here, to perform RAIM capability function, it needs 5 satellites in view, 4 for position, and nav plus 1 extra must be tracked. So it's basically assuring that we have 5 satellites available that will be in view along our entire route at the time that we're flying. If not, it'll give us a RAIM alert to tell us that we cannot use GPS or any satellite-based technology on that flight. Now it almost never comes back, not having at least 5. It's really rare to have a RAIM check fail. But every time you send a dispatch release, it does what's called a RAIM check. And the RAIM check basically checks the route to make sure that we'll always have 5 or more satellites in view during the entire flight. And as long as that's okay, it'll come back as saying RAIM check passed, and that means that for that flight we're okay to use any type of satellite-based technology. So, but that's how it works. And like I said, it's rare for it to come back and not have it. So, and if it does say it failed, it's usually an error, and then if you do it again, it'll usually pass. Sometimes you have RAIM outages, and that's just simply because sometimes they take one of the satellites out to fix it or whatever, which is also rare. But RAIM messages, not enough satellites available to provide RAIM. RAIM detected a potential error. Causes of RAIM outages are insufficient number of satellites, poor satellite geometry, leads to large position errors. Change in aircraft dynamics, such as banking, obscures the GPS satellite signal, which must be received line of sight. GPS IFR certification requirements. This is just basically telling us what standards GPSs need to meet in an airplane in order to be able to be used. So when it says IFR, that means to use in instrument flight rules. So that means, everything we do in the dispatch world is IFR. All of our flight plans are filed IFR. So when it says that it meets IFR certification requirements, that means, one, that it meets the requirements of the type of filing, the flight plan filing that you'll be doing, because everything we do is IFR, but also what IFR literally means, though, when they're up flying, they can be flying in instrument rules, which means that they can have no visibility. They can fly through clouds to where they do not have to maintain visual reference to the ground or to terrain. So that's what IFR is, though, is being able to fly and still losing your visual reference to the ground and to surrounding terrain. So, because if you file VFR, remember, you always have to maintain the visual references. And as soon as you lose the visual references, if you do lose it, if you accidentally flew into a cloud or something on a VFR flight, you have to immediately exit, obviously immediately exit that condition. So let's see. Yeah, most of this stuff we don't need to really read over. So GPS, IFR, in-route, and terminal navigation requirements. In-route navigation must have an alternate means of navigation appropriate for route of flight to destination and your alternate, meaning a ground-based nav aids must be operational. So for whatever reason, It's kind of just, if you think about just kind of the really more of a government thing, government kind of gets stuck in the past and using outdated technology. But because of our systems our governmental systems here in aviation, they still make us, they basically don't let us solely rely on GPS or satellite. They basically say that in order for us to use it, there has to be a ground-based backup wherever we're going. So I don't know why they do that, because ground-based technology is far more inaccurate than satellite, and it's far more unreliable than satellite. But you could fly a flight with only having ground-based and no satellite, but you can't fly one with only having satellite and no ground-based navigation aids. So it's basically just saying that we always, if we're going to use satellite navigation en route, we always have to have a ground-based backup wherever we're going. Yeah.
How long have we been using GPS?
Oh,
Long time now?
long time now, yeah. So it's just kind of one of those things that just kind of gets stuck in the bureaucracy of changing how things are done, But obviously, anybody who's has, half a brain at this point in life that knows anything about GPS and ground-based would be able to tell you that it's far safer to have satellite only with no ground-based than it is to have only ground-based, with no satellite. So
before GPS, were we actually using VORs for high altitude flight?
yeah.
Wow.
Goes all the way back to using those arrows that we looked at, For airports, you must have non-GPS instrument approach procedures. That's what the IAP stands for. If alternate instrument approach procedures requires ADF DME, must have it on the aircraft. So it's just basically saying that we have to have ground-based backup wherever we go. Now that is changing, as we move on and progress in the aviation world. A lot of airplanes now, I believe now we're to the point where as long as you have two systems in the airplane that are both have satellite technology, as long as you have one primary and one backup, we can now go to places that don't have ground-based technology or VORs or things like that, which is going to be the way it is in the future. Obviously, they're starting to kind of do what they did with the NDB system, is kind of starting to phase out. They're doing that with the VORs slowly. So slowly you're going to see the VORs go away, and you're going to just see everything will be satellite with no ground-based, because it'll just slowly be, once it breaks, they won't fix it type thing. You have these other ones called WAS and LOS. These are types that you can list on types of satellite navigation. Wide and local area augmentation system. What it is it is an upgraded version of GPS. It improves accuracy, integrity, and availability of GPS signals. It uses receivers use two geostationary WAS satellites. Performance enables instrument approach procedures with GPS WAS glide paths, GPS precision approaches with vertical guidance. It'll give you lateral precision approach with vertical guidance. A lot of this stuff you probably don't know what it means yet, but you will. What it means when it says precision approaches with vertical guidance, it basically means that as you're approaching a runway, you can tune in, you can use this WAS system, and it'll guide you vertically and horizontally. So it'll tell you if you're coming down to land on a runway, it'll give you like a glide path that you just need to follow, and it'll take you right down, and land you exactly right on the runway, following a signal basically. And there are other ground-based systems that do this as well, but this is the satellite version of basically what does this. So, but you'll learn about what precision approaches are actually here when we start looking at the ILSs and things here shortly. But all WAS is just a more accurate local system that's used for airports and to use for instrument approaches like approaching or like landing approaches and stuff. This kind of gives you an idea of how it works, although it's probably a little confusing to look at. But if you can think of like if you are in really, really bad weather where you're trying to land at an airport and you cannot see the airport. I showed you guys that video, right, on the first day of that when I was in the jump seat. So that's kind of an idea, like, of what I'm talking about. Like, if the weather's really poor, you can follow this guidance system, and that's what they were essentially doing when I was in the jump seat that day. Is they were following that guidance system down, and it was guiding the plane right down to exactly where they needed to be, even though they couldn't see anything. Once they could, it just suddenly appeared the runway, and they're like basically, less than 100 feet at that point from touching down. So that's what this WAS system does as well. Same idea. It navigates the plane right down to exactly where it needs to be. That's why it's called a precision approach. It gives you the precise guidance in both vertically and horizontally. So the inertial navigation system is a computer-based navigation system. It tracks movement of aircraft via signals produced by onboard accelerometers, fully self-contained, initialized by the pilot before flight enters in-system location of aircraft on the ground. It navigates without any input from outside aircraft, and it's programmed with waypoints along the route of the flight. So this is a little bit more rare to use this. It's kind of, it's just something that kind of exists, but we don't really use this in any of the planes that you'll ever be dispatching. So other than just knowing it exists, that's about it. So if just INS, inertial navigation system, that's really the extent of what you need to know about it. Flight support systems. In the airplane, you have air data computers. And what those do is they process pedostatic pressures, temperature. They calculate your altitude, your indicated airspeed, your true airspeed, your air temperature. In order to fly into RVSM airspace, 2 are required and must be operational. So, what's that?
Those are my parts on the charger.
Oh, the air data computers?
They're all running computer time. So go backwards and forwards and how much of a pain all those pieces are.
So how many does each of our planes have?
Air data computers,
Yeah.
2.
2 on each one? Sometimes I wonder if we had like more, like if there was like 4 or something, like backups.
They get moved around a lot. Changed.
Yeah, that I see, yeah, like.
So it might seem like there's a million of them because you'll have them put on and taken off 5 different times.
Yeah, and do they have to track like which airplane it's currently on, right?
Yeah.
And how many hours it's been on them.
Here's a little side question for you guys. That's just something that I've always wanted to know. I'm not sure if you guys know the answer to this or not, but do you guys ever deal with anything of when we like return a plane, like a lease return? So does it have to be, somebody told me one time that all of the parts on the airplane have to be returned to the originals. Is that anything you guys have ever heard?
I can't
know about
imagine
that.
Yeah.
It seems like it would be
Because a lot
totally
of them
unreasonable.
are sent back to the vendors. Like a lot of times we don't ever have the same part back. Like if it breaks and the vendor can't fix it, they'll send us a replacement part.
Uh-huh.
So sometimes we may not even have the parts that it came with.
That makes
Plus, when
sense.
we receive planes, we receive all the information that the last owner has.
Yeah.
So I can imagine that if we had to give one back or sold it to someone else, we'd just give them all the information and all the history that we have. I
Which
can't
is what
imagine
we
they would
do.
ever
We would,
put the original, because they steal parts all the time.
yeah,
Yeah.
We'd have
so the
one
parts would
on
be
it
scattered
used-
on a bunch of different planes.
Yeah, so if we had a part on an aircraft that we were using, there's no way we could take it off of that aircraft, put it back on this one we're
It'd be a
selling back.
disaster.
Yeah.
There's just
Well, and that's what I figured, because I figured it would be a total headache. But yeah, somebody in maintenance control told me that one day, and I was like, that seems a little.
But maybe they don't rob parts from planes they know are going back. Yeah.
Maybe, but there was
But
one,
even
and maybe it's just certain parts. Maybe, I don't know. But there was
like
one
life
time
limited parts.
that we had to, somebody said that we had to take a part off of an airplane because the part that it had was one that was going to be lease returned the following week. So it had to be swapped out because it needed to go back onto the original plane. And it might just be select parts. I don't know.
Maybe how it's tracked, so.
Maybe.
Some are tracked by cycles, some are tracked by hours, some are tracked
Yeah.
by,
Months
you know,
or
just
days.
its whole lifespan, so it could be any one of those.
Yeah, I look in that
Whatever.
SkyTrack system all the time, like looking at not so much for part stuff, but like when the inspections are due and things like that. So
Which is what his wife does.
yeah.
It's kind of interesting.
Yeah. Yep.
Anyways, enough about air data computers, let's stare at them all then.
So those things basically just calculate all of the altitude. It just takes a bunch of the different stuff, the readings that the plane has, and it calculates a lot of different information. But the big ones are the altitude, the indicated airspeed, the true airspeed, and the air temperature. Flight Director System combines several instruments into one display. Provides easy interpretation of the flight path, and it uses the ADI, the attitude direction indicator, the HSI, the mode controller, and the flight director computer. And it basically just it's taking a bunch of the different components on the aircraft, and it's using that to help display visually, because on all of these planes that we use, you know, they have the graphical, they call them glass cockpit displays. So it's showing you more of like a computerized image of like your where the aircraft sits positionally, you know, speaking. It also shows like your flight path. There's a lot of different things that it shows, stuff that we'll get into with systems, but the flight director system is just basically giving you kind of an idea of the accuracy of all of your systems combined into one, giving you your heading and displaying that all kind of in one display for you. Integrated Flight Control System integrates various systems into one system operated and controlled by one component comprised of airframe, the flight director system, and the autopilot. The autopilot controls the RVSM. One is required and operational, but it monitors the yaw, the pitch, the roll, an electrical, hydraulic, and digital system. So this is kind of the same idea as the last one, where it's just basically one system that's combining several systems into one, and it works hand in hand with the autopilot. But going back to the RVSM thing, there's several systems that must be working in order to go into RVSM. Autopilot is one of those systems that must be operational. Otherwise, you cannot go into the RV, or you can't go above 28,000 feet. You can't enter RVSM airspace. But we'll also review that later as well. FMS. FMS is the Flight Management System, and this thing is probably the single most widely used system on the entire aircraft. The FMS is something you will see on quizzes, so do know what this is and what it does. You'll also more than likely get FMS questions on your practical exam from the FAA examiner. Every one of these guys that recently took the FAA practical told me that he asked about FMS on every one of them. So thought that was kind of interesting. But anyway, what it does, it's a master computer, interfaces with all the navigation sensors. The GPS is the dominant FMS navigation sensor, and what it does is it takes all these things, kind of the same as the last two things we looked at, but it puts everything into one, and one what's called control display unit. And it interfaces with the master computer and provides single control point for all navigation systems. So whether you're using RNAV, whether you're using GPS, whether you're using even the VOR, DME, any of that stuff, it actually is all controlled and read by this FMS. So it's taking literally anything you can think of navigation, whether it's satellite navigation, whether it's ground-based navigation, it all runs through the FMS. And the FMS takes all of that information and it spits out on one display, what it's using, where it's located, and on your flight path, it calculates everything for you that you're basically looking at. It uses an electronic database of navigational aids, airways, SID, stars, and instrument approach procedures. If you remember SIDs and stars we talked about a little bit last week, that's a standard instrument departure and a standard terminal arrival route. So it has all of those routes built into it, and every 28 days it gets updated. So a lot of times you'll see an airplane that has an out-of-date navigational database. That means that the 28 days were up, that it was supposed to be updated, and it didn't get updated. So you'll see the FMS will be labeled as inoperative. They can't use it because it's outdated. So all they got to do is get the company that services it to hurry and hook up their computer and update it. Takes like 5 minutes, but anyway, sometimes it goes over the 28 days. It inputs everything into the control display unit to create a flight plan, provides the data on a display, it commands the aircraft where to go, and it provides the lateral navigation and the vertical navigation guides on an instrument approach procedure. So that's what an FMS does. FMS is one of the biggest things we use, though. The FMS also interfaces with other aircraft systems and provides fuel management, displays other systems, graphical weather displays, and it also operates the ACARS link, which is the air-to-ground data link communication. So when they are text messaging us back and forth, they're typing it into the FMS unit. And that FMS unit is what it goes into the ACARS system and sends the messages back and forth to the dispatchers.
It's kind of funny. A lot of the stuff that's the most important as far as parts go up in dispatch are the ones that we just we don't care about that.
So like what do you mean by that? Like from your side though, like they don't.
Like the FMS, we just audit next. We just kind of throw it away. If there's anything about ACARS, we just throw it away. If the crew O2 is low, we don't care.
Yeah, we just don't track those things. So we just kind of acknowledge that they were done and skip over them.
So, but meaning just acknowledging that they were fixed, or if somebody said that it was done, then there's no, other than just them saying it,
there's a
check the
record
box.
of it, but we don't track it or do anything with it. So that's why
I think it's because a lot of those systems I think the tracking is done by the vendors. So that's probably why, like on the FMS units, like the vendor that does the database uploads, they're the ones that actually track it, because they'll send us emails saying, hey, this aircraft is out of date now. Mm-hmm. And then that's how we know. And then same with the ACARS. The ACARS it's all done by AirRink. It's all saved, that company. So anyway, maybe that's why. But ultimately, the FMS is looking at, it's basically the thing that runs the entire aircraft. The EFIS, which is the Electronic Flight Instrument Display. So you can see here, this is the inside of the airplane here. It basically replaces, so this one display replaces numerous mechanical indications with a glass display. So this is your primary glass cockpit type technology. So what that means though is if you get into an older aircraft and you get into it and you look at it, if anybody's ever seen one or seen pictures of one, you'll just see a whole bunch of like gauges, not necessarily any like computer displays. You'll just see a whole bunch of circular gauges everywhere that they look at. Well, what this EFIS thing does is it takes all of those things and puts them, reads all of them, and it can display, like you can toggle different pages on this display and you can see all of the systems by scrolling through it, basically. You still have a lot of those other gauges that you used to have, like, you know, all of the hundreds of, you know, circular gauges everywhere. You still have some of the ones that you need in case you lost electrical power and in case some of this stuff stopped working mid-flight. You have the essential things that you need. However, a lot of the stuff that can be done away with that you can just, you know, put all into one system and then scroll through it when you need it and have it be visible if you need it and not visible when you don't, is all in kind of munched into this whole electronic flight instrument display.
Is that what cockpits look like now?
Yeah.
Nowadays, mostly?
Yep.
Interesting.
Yeah, that's actually pretty much exactly what that's pretty much that's the airplane that we are doing in this class. That's the cockpit of that plane. So when we do our airport tour, we'll go into the airplane and everything and look around in it and go into the cockpit. It'll be a 200 that we go into, but it essentially most of the things are the same. It's just a smaller plane. Instrument approach systems. The first one we're going to look at is ILS. So ILS stands for Instrument Landing System. When you look at ILSs, there are 3 different categories. There's Category 1, Category 2, and Category 3. The only thing that you guys need to be concerned with in this class is Category 1. Okay? Category 1 is going to be the only thing that we use in this class. We won't go any lower than that. So if you see, well, you'll know what Category 2 is, and Category 3. They're just basically lower minimums of the same thing that we're looking at here. But Category 1 means, or what it is, first of all, it's instrument rated, so it's the aircraft, if it has ILS equipped technology in it, it basically will allow that aircraft to fly down to a minimum of a half-mile visibility or 2,400 RVR. That RVR is your runway visual range. That's what that stands for. And a decision height of 200 feet. So what that means from an airplane perspective is that the weather could be that, like if your weather, like if you're looking at your weather report for wherever you're about to land, if the weather could be as low as a half of a mile or a 200-foot ceiling. So when you look at RVR, that's just basically a foot measurement of your visibility. So if you see half mile, 2,400 RVR is essentially the half mile equivalent of just RVR in feet. That's all you're really looking at there. RVR though, when you're looking, or if you get an RVR report, it always is going to trump the other. So if you get half mile and then 2,400 RVR, The one that is the controlling is going to be the RVR. So a lot of airports, well, every airport will have the visibility listed in statute miles, okay? Only some airports have RVR technology though. But if you are going to an airport that has RVR reports available, the RVR is going to be the controlling visibility report. So if you see half mile or an RVR report, whatever the RVR says is going to be the one that you have to go off of, if that makes sense. So if you're about to land and the pilot's checking the weather, or you as a dispatcher's checking the weather, and you see that the weather is below a half of a mile, let's say it's a quarter mile, then that means that it would be below ILS Category 1 minimums. So when we look at this criteria that it's giving here, these are weather minimums that it's telling us. So a half mile is the Category 1 limit. That's as low as you can go down to visibility-wise and still land. So if it's below a half mile, then you basically can't land the plane. You can't shoot the approach essentially, or even fly down it. The next part, that thing that says DH 200, that's decision height 200. That means a ceiling or a cloud-based ceiling of 200 feet. So if the ceiling of the clouds is below 200 feet, same idea. That's the minimum that it can be. It's got to be 200 feet or higher. The visibility has to be half mile or higher. So that's the lowest instrument approach that we will deal with in this class. So
What's DH again? I'm sorry.
decision height.
Okay.
Don't get necessarily too worried about a lot of these visibility and the decision height stuff, because this stuff we're going to look at over and over and over once we start getting into looking at approach plates and things like that. When we're looking at each of our flight plans, you're going to have to look at this stuff. So this will be something that is repeated pretty extensively throughout the rest of the class. So, but just for now, the only thing you need to know is ILS Category 1 weather minimums are half mile and 200-foot ceiling. That's pretty much it. The next one is a Category 2. Like I said, we're not going to ever do Category 2 in this class, so you don't really have to worry too much about it. Category 2 is something that you'll learn about once you actually dispatch real life, get it on with an airline, and do it, there. You'll learn a little bit more about it and what it takes. But just as a general thing, Category 2 is a quarter mile visibility and a 100-foot ceiling. That's kind of the way to look at it. 1,200 RVR is the lowest. SkyWest, just on a side note, SkyWest, the lowest that SkyWest could do it as an airline is a Category 2 ILS. They can go down to 1,200 RVR and a 100-foot ceiling. That video that I was showing you guys was basically I think it was right at 1,200 RVR. That's what the tower told us the RVR was right before we started the approach. So if it was anything lower than 1,200, we wouldn't have been able to even start the approach. We would have had to just sit there and hold and wait for it to come up. But ATC said RVR 1,200, cleared to start the approach. So anyway, like I said, in this class, we're not going to do anything that's Category 2. We're just going to stay Category 1 or higher. Category 3 is even more so. Like Category 3 is your big airlines, your mainline, your big jets. They can go down to Category 3, which even within Category 3, there's 3 different categories. There's Category 3A, 3B, and 3C. And what those are is Category 3A is a 700 RVR, Category 3B is 150 RVR, and C is 0. So, and then no decision height requirement, meaning that there is the only thing, they don't even look at the ceiling with Category 3. The only thing they care about is the RVR reading. That's it. So 3A is a 700-foot reading, B is 150, and C is 0. So if you're thinking Category 3C is technically you can't ever see. You just land. you will feel the plane land before you see the ground. But planes can do that. Planes are, modern day bigger planes are equipped with what's called auto land, and they can just turn it on auto land and they can land in category 3C conditions. So it's pretty crazy. You can probably YouTube some category 3, just search for category 3C landings, and you can see some. Kind of a little crazy thought, but some of the really big planes like 747s, A380s, even if they're not shooting a category 3 or a category, even in a category 1 approach, which is category 1 is pretty standard. Like you don't even need special certification to do it, or if you're an instrument rated pilot, you can shoot a category 1 approach in your little Cessna plane if you wanted to. But a 747, if it's going down, shooting a really low visibility approach, and if it gets down below 300 feet, they say, or sometimes 200 feet, and if they still can't see, they make that decision to where they're not going to land, and they do what's called a go around, where they throttle back up and they climb back out, and they try again essentially. But on a really heavy plane, once you get below, I want to say it's either 300 or 400 feet on like the A380s. Everybody knows what an A380 is. The big, huge, the whole thing's like a double-decker plane. Like 300 or 400 feet on that plane, and like a 747, like anything under like 200 to 300 feet. By the time they even make the decision that they're going to go around and throttle back up, a lot of times, just in the time that it actually takes to spool back up the throttles and the engines to go back to high power, by the time that they even do that, their back wheels a lot of times still usually hit the ground as they're going back up, even though they still take back off. Like it's just really weird to think, because a lot of times they'll still touch even though they're going back around. So what's that? Must be 8:45. Yep. ILS are composed of what's called a localizer, a glide slope. Those are the two main components of an ILS. So know what those two things are: localizer and a glide slope. Localizer gives you your horizontal guidance. That would be your left to right. And a glide slope gives you your vertical guidance, up and down. So an ILS is a ground-based navigational aid, okay? So now we're kind of circling back a little bit, back to specific instrument approaches. So when we first started looking at like VORs, NDBs, those are the things like you're kind of using more en route. Now we're looking at stuff that we use when we actually go to land the plane. So once you get close to the airport, you tune into this ILS system, which aligns you with the runway. It also tells you, it has a little path that you follow, and this is all based on ground-based technology. Kind of the same idea that we were talking about earlier with the WASP satellite system. It gives you the vertical and the horizontal guidance so that the plane knows exactly where it needs to position itself, and the plane will follow that. It actually shows up as like a little marker that, it'll show you left, right, and up, down. The two things, it's like two crosshairs that will cross right over each other, and you just need to keep those two crosshairs aligned as the plane goes down. If the one starts to go up, that means you need to pull up. You're too low. Or if it starts to go low, you need to push down. So you're basically just following that as the plane is going down, and you just want to keep those things perfectly aligned. As long as you do that, it'll position you right out where you need to be to land the plane. And you can follow that down. A standard ILS Category 1, going back to what we were talking about, once you get 200 feet off the ground, If you cannot see the runway, then at that point, based on the Category 1 minimum, if you can't see it at 200 feet, then you would need to go back around. Like you couldn't land, essentially. So, and that's the lowest, like I said, that we'll use in this class.
This is all ground-based stuff.
This is ground-based, yeah. And the ILS, when we go out to the St. George Airport, we'll look at their ILS. We'll look at all this stuff, too. We'll look at the VOR, the ILS, the localizer. You'll see all of this instrumentation out there. But anyway, yeah, it's just an ILS is what's called is one of the precision instrument approach systems. So you have precision and you have non-precision. Non-precision approaches give you horizontal only. Okay, so write this down. This is also something you need to know. You might be asked, what's the difference between non-precision and precision approaches? Non-precision is going to be horizontal guidance only, and precision is both horizontal and vertical guidance. ILSs can also give you like DME. It can give you, that different types of alignments to know how far out you are. You can read in the airplane. So a few other things that are on there, but instrument landing system. You'll also be asked questions like, name a couple of different types of non-precision approaches and name a couple of different types of precision approaches. ILS would fall into the category of a precision approach. So let's look at the next one here. This is still looking at ILSs here. Kind of just giving you kind of a further outline detail of how it works. For what you need to know, the only thing you need to know is what an ILS is and that it gives you both horizontal and vertical guidance. You don't need to necessarily understand the system itself and all of the technology behind it. You just need to know that it's ground-based, it's a precision approach, and then know those Category 1 minimums, the 200 feet and the half-mile visibility. A localizer is a type of non-precision approach. Okay, so not to be confused, when we were talking about the ILS, there's two components of the ILS, the localizer and the glide slope. You can use that localizer part of the ILS, you can use that just by itself, and it's called a localizer only approach. And if you do that, if you use just the localizer portion of the ILS, then it's considered a non-precision approach. It has higher minimums that are associated with it, but it just gives you just that horizontal guidance. But it's using just that one portion of that half of the ILS. A lot of times you'll have, and like I said, just like as is common with any type of ground-based navigation, a lot of times different elements of it doesn't work. So if you have an ILS that has the glide slope out of service or not working, then that ILS suddenly becomes just a localizer approach only. So it turns itself from a precision to a non-precision approach. So, but you can also, even if the full ILS is working, you can still use just the localizer portion of it if you wanted to. So some airports have just a localizer with no glide slope. So that's the reason why we're kind of seeing it on here. So because it exists, you'll see different approaches for just a localizer. Then you have the glide slope, which we already talked about, but it's just basically giving you the vertical guidance. If you want to learn more about it, you can circle back to this slide and read all this stuff. This is talking about marker beacons. However, there's really nothing you need to know about marker beacons anymore. They're actually now a thing that's not really used on ILSs anymore. So I'm not going to worry about having you guys look at it. Some ILS systems also require a certain type of approach lighting systems for the airport to have in place in order for it to actually qualify as an ILS. So these are different types of approach light systems that you can have at an airport, all of which are related to basically having an ILS approach. So some of these things, simply the more type of lights you have, the more guidance it gives you. But most of these here are, like for instance, all of these can be used on a standard ILS. Once you get into like these ones over here, like this one on the far left and then this one here, the second one over, these are more used for the Category 2 and the Category 3, like the lower minimum ILS approach procedures. Garrett just asked a question. He says, one of the questions on the ADX does ask what happens if the middle marker is out on a straight-in approach. Yeah, and so the answer says that it doesn't have any effect. So, and the truth is nowadays, if any of the outer marks, see, now remember the ADX, once again, I know we've kind of covered the ADX stuff a lot. The ADX is very outdated, and a lot of the questions now don't have anything to do with modern day dispatch. So although that was a correct answer, well, and it still is a correct answer, but if you were to get asked, like, so this question was, if the middle marker is out on an ILS or a straight-in approach, what happens? It's no effect. But nowadays, if any of the markers are out, whether it be the outer, the middle, the inner, any of them are out, it has no effect anymore. So those are the different types of approach light systems. You don't really need to worry too much about that. Types of localizer approaches. You have one that's called an LDA, which is a localizer directional aid. It's not aligned with the runway. It's the same thing as an ILS. The only difference is that it doesn't bring the aircraft straight in. So St. George technically does not have an ILS. It has all of the equipment that an ILS has, except it's actually called what this is saying here is an LDA. And the reason why some are LDAs and some are ILSs is because it here in St. George, because of the mountain that's straight out here, like straight off the end of the runway, Pine Valley Mountain specifically, because of the proximity of that mountain to the airport, here in St. George, we can't technically do a straight-in ILS system because that mountain is too close for that angle of the approach to come down over the mountain. It gets too close to the mountain. So in order for them to accommodate that, they had to change their ILS into what's called an LDA. And all an LDA is it shifts the approach system to offset a little bit. Instead of it bringing the aircraft straight in, it still does all of the same things. It brings the aircraft down. It is a precision approach still, except it brings the aircraft down in. And once you can see the runway, you're not straight aligned with it. Like you come down at an angle. So if you're coming down like this, and it can't be more than 3 to 6 degrees, but you come down looking this way, and the airport might be, or the runway might be straight this way, and you're coming in like this. So once you can see the runway, you just need to do a tiny little turn and then land. It still is a precision approach. It still has the horizontal and the vertical guidance. But it's just not, it just doesn't bring you straight in. SDF, don't even worry about that one. You never really ever see it. And then you have the localizer, and then you have a localizer back course. Localizer back course is just it's just using the localizer, the same one on that you use on the regular localizer. It's just that you're using the opposite end of the runway. That's all it is. You have a microwave landing system. It is a precision approach, except it's similar to an ILS. It uses all of the horizontal and vertical guidance systems, except this allows for curved approaches. It's very expensive, and it's also very rare. The only thing you need to know about it is that it's a precision approach. I doubt you'll ever see one at any airport that we dispatch to, or that you'll ever dispatch to, but it is a precision approach. So when you get asked the question, list a couple of different types of precision approaches. You can put MLS, or you can spell it out, microwave landing system, but it's just similar to an ILS, and it's just more expensive technology, and it allows, like it shows, for the curved technology, or the curved approach path. And then you have RNP, which is a type of satellite navigation, except RNP is a precision approach using the satellite, kind of similar to the WAS that we looked at earlier. It uses the RNAV, onboard navigation, alerting. It uses a new standard of navigation and airspace management, navigation performance required within a defined airspace, RNP navigation performance necessary for operation within a defined airspace, aircraft navigation system ability to monitor its navigation performance and to identify if operational requirements are met. All this is really saying is that in order to be able to use it, the preciseness, I guess you could call it, of the satellite coverage or navigation has to be precise to within a certain amount of nautical miles. Like, it usually has to be precise to within 1/10 of a mile, or precise to within 1/2 of a mile. Like, there's different RNP levels that they use depending on the type of approach. But some, if you're flying an RNP approach, and once again, this is a precision approach, it's using satellites, nothing ground-based, but it's using vertical and horizontal guidance, except the only thing that you have to look at with RNP approaches is that you have to look at the precision requirement, which is just basically telling you it'll be like a 0.1 or a 0.5, and that just means 0.1 meaning 1/10 of a mile, 0.5 meaning 1/2 of a mile, or whatever it says. It'll say point something, or sometimes it'll even say 1.0, meaning precise to within 1 mile. That means whatever the signal it's receiving from the satellite, it has to be precise to within 1 mile of your location. Now, 1 mile is obviously pretty lenient, if you think about it. Like, if you're 1 mile off and you're flying an approach, obviously that's bad, right? Now, if you're up in the air and you're 1 mile off, like flying en route, not a huge deal. Like, it just depends on where you're at and what the terrain is around where you're at. Depends on how precise the signal needs to be. So if you're flying like down a canyon where you've got 200 feet this way is a canyon wall, or if you're 200 feet this way, same thing. Obviously, the precision of the guidance system has to be probably the most precise it can be, down to the best that they have. So a lot of it, you don't see RNP approaches very often. You see them in like areas, like you see them a lot up in Alaska, in areas where you're flying down canyons and channels, things like that, where there's a lot of terrain around that you have to navigate around, and they don't have a lot of ground-based, nav aids up there. So that's what RNP is. It's pretty much the best type of satellite approach performance that you can get. So that would be listed with satellite-based under the precision category. This kind of shows you. So it shows you right here, RNP 1.0, RNP 2. So this would be the different requirements. On a departure, you might need RNP 1.0. During the en route, you would need maybe RNP 2.0. The arrival 1.0, and then the approach down to 0.3. So it just kind of gives you an idea, some examples of when and where you would need the different types. Heads-up display, we don't really need to look at that. That's just for approaches that are Category 2 ILS and lower. Safety systems, radar altimeters. That just basically is an additional radio component on the plane that actually sends a signal to the ground to calculate how far above the ground level you are, in addition to your regular altimeter. So this is something you use when you're flying an approach to have like double and triple accuracy on your actual height above the ground, just in case your regular altimeter was off. And then you have, and I believe this is the last thing we actually look at here. Yeah. Oops. Sorry.
This low.
This thing is really going slow. Terrain alerting and warning systems. These are just used. We're going to look at these more in systems, so I'll just quickly mention them and then we'll be done. But ground proximity warning system. There's a bunch of different systems on the plane that just basically tell you if you're approaching terrain, if you're approaching the ground, if your landing gear is not down and you're more than 200 feet off the ground or less than 200 feet, you'll get these warning messages that'll come up. They're verbal warnings that'll actually come up into the cockpit to tell you, pull up or terrain. Yeah. Yeah. They also is that same system that in our, when I had that video, you can hear the thing calling out the altitude levels, where it says 50, 40, 30, that's all comes from this system. It's calculating your altitude and it's telling you where you're at. But it's used for a lot of different things. It's the same system is used for the wind shear alerts, for the microburst detection stuff, for traffic, for if you have another plane that's too close to you, it'll actually come on and it'll tell you traffic, and it'll give you an advisory that you need to turn this way. And this system actually, other planes that have the same system, they all talk to each other. So if you're flying by another plane that has this same system, those two talk to each other. And if you're flying too close to each other, it'll give you both a warning and it'll tell you to turn right and it'll tell that guy to turn left, so that you're turning away from each other. So it's kind of cool. We'll learn more about it later. But it's called a TCAS. Part of it's called a TCAS system, which is just another acronym that you'll learn later. So that's pretty much it. Fun day? Hope so. So yeah, that's it for today. If you guys want to review this again, I'll put it up on the thing. But if you guys get on this and you have problems using it off the Google Drive, let me know so I can just email it directly to you guys instead, if it works better.
So what was another precision approach at ILS, MLS, and what was the rate of the
RNP.
RNP?
Yep.